You know that feeling, right? You walk into a room and, everything just feels perfect. Not too hot, not too cold, just right. We've all felt it, but have you ever wondered what's really going on behind the scenes? Well, in this explainer, we're going to pull back the curtain on the hidden science that creates that perfect feeling of comfort.
So here's a mystery for you. The thermostat on the wall says 72 degrees, but for some reason, you're in the living room reaching for a blanket, even though you were totally fine in the kitchen a minute ago. What gives? Well, the answer is way more interesting than just a number on a thermostat.
Okay, so to get to the bottom of this, we first have to ask what even is comfort? Because as you're about to see, it's a lot more than just a feeling. It's a science.
Now check this out. The official definition of thermal comfort is a state of mind. How cool is that? It means it's partly psychological, but you could get to that state of mind through a very real physical balance. The goal of any heating or air conditioning system isn't to change your body temperature. It's to control the rate at which your body loses heat to the world around it. That is the absolute key.
So, how do engineers control that balance? Well, they've got 4 main tools in their toolbox. We all know the first one, air temperature, but it's these other 3, radiant temperature, humidity, and air motion, that are the invisible players, the real unsung heroes making all the difference. Let's think of them as the main characters in our story today. To really understand this whole thermal balance thing, we have to start with one half of the equation, and that's you. Because, and I mean this in the best way possible, you're basically a walking, talking furnace. Every single second of your life, your body is burning fuel, the food you eat, in a process called metabolism. But here's the wild part. Only about 20% of the energy you generate from food actually goes toward things like moving your muscles or thinking. The other 80%, it's just waste heat. It's like the constant exhaust from your body's engine, and it's running 24/7.
Okay, so your body is constantly producing all this extra heat, and it has to get rid of it somehow. How does it do that? Well, a little bit is lost through convection. That's just air moving across your skin. A bigger chunk is lost through evaporation, which is just a fancy word for sweating. But look at this chart. The undisputed heavyweight champion of heat loss is radiation. A whopping 60% of your body heat is lost this way. We're going to come back to exactly what that means because it's super important. And get this, your internal furnace doesn't just have one setting. When you're sleeping, you're putting out about 100 watts of heat. But if you start jogging, that number skyrockets to 800 watts. This is exactly why a crowded gym or a packed concert feels so warm, even if the AC is on. It's not your imagination. The room is literally filled with hundreds of human-sized space heaters working overtime.
So, we've established that we're all walking furnaces, constantly giving off heat. But how does that heat actually get from our bodies out into the room? Turns out, physics has 3 fundamental ways this can happen. First up, you've got conduction. This is the simplest one to wrap your head around. It's just heat transfer by direct touch. You grab a cold can of soda, and heat flows from your hand to the can. On a microscopic level, the vibrating molecules in your hand are literally bumping into the molecules of the can and passing along their energy.
This classic teacup example shows it perfectly. The hot tea gets the molecules at the tip of the spoon all riled up and vibrating. They bump into their neighbors, who then bump into their neighbors, and so on. It's this chain reaction of energy that marches right up the handle of the spoon, even though the metal atoms themselves aren't actually traveling.
The second way heat moves is through convection. Now, this is a little different. Instead of molecules just passing energy along, with convection, the hot molecules themselves actually move from one place to another, carrying their heat along for the ride. This always involves a moving fluid, like air or water. You've seen this a million times. You know that wavy, shimmering air you see over hot pavement in the summer? That's convection in action. The road heats the air right above it. That hot air expands and gets lighter, and it rises up, creating a current that carries heat away. A cool breeze from a fan? That's convection too. And the third method is radiation. Remember, this is the big one for our bodies. Radiation is how the sun warms the Earth from 93 million miles away, across the vacuum of space. The heat travels as invisible electromagnetic waves, just like light waves or radio waves, and it doesn't need to touch anything to transfer its energy.
A fireplace is the perfect analogy. Radiant heat travels in a straight line. If you have a clear line of sight to the fire, you feel its warmth because your body is absorbing those energy waves. But if you duck behind a big armchair, you block the waves and you don't feel the heat. And this is the key to our original mystery. Why do you feel chilly next to a big window, even in a warm room? because your body is literally radiating its heat out to that cold glass surface. The air isn't cold, but you're losing heat, and that makes you feel cold.
Okay, so if we're all these little furnaces constantly losing heat in these three different ways, how do buildings manage this complex stance to keep us comfortable? Well, it really all comes down to two main strategies. On one hand, you have thermal capacity, or mass. Think of this like a heat sponge. It's a material's ability to soak up and store a ton of heat. A heavy cast iron pan is a perfect example. It takes a while to heat up, but once it's hot, it stays hot for a long time. On the other hand, you have thermal resistance, which we usually just call insulation. This isn't about storing heat, it's about stopping the flow of heat. It's your winter coat, full of trapped air pockets that keep your body heat from escaping.
And you can see these two completely different strategies at play in the real world. In a hot desert, a traditional adobe building is all about high thermal mass. Those super thick mud walls spend all day absorbing the sun's brutal heat, which keeps the inside surprisingly cool. Then, when the desert gets freezing cold at night, the walls slowly release all that stored heat back into the room. It's brilliant. But a ski lodge in the mountains? It has the opposite problem. You want high thermal resistance, lots and lots of insulation to trap every bit of heat you generate inside and stop it from leaking out into the cold.
So, what all this shows us is that creating that just right feeling isn't some happy accident. It's a deliberate, calculated, and pretty amazing process of engineering. Engineers follow this really rigorous process. They start by analyzing everything: the local climate, the building's shape, what people will be doing inside. Then they calculate all the thermal loads. That means every source of heat gain, from sunlight to computers to people, and every source of heat loss. It's a huge, complex equation, and only then can they design the systems to perfectly balance it.
Ultimately, the goal is to create these carefully controlled zones. An office building, for example, might have one zone for the sunny side of the building and a completely different one for the shady side. A crowded conference room needs a different setup than a single quiet office. Each zone is its own little ecosystem designed to tame that invisible flow of heat and satisfy the people inside.
So the next time you walk into a room and it feels just right, take a second. Don't just feel it, see it. Look at the windows. Notice the airflow from the vents. Consider the materials used on the walls. You'll realize you're not just standing in a room. You're standing inside a carefully tuned machine designed for the sole purpose of creating that perfect, invisible balance between your inner furnace and the world outside.